system or machine is transiently stable if after a severe fault or disturbance it can regain synchronism. That means returning to the synchronous speed. What does it mean actually? This is the transient stable system. Let's say we have omega versus t curve. Whenever we will start at the initial point, our system is in the steady state phase. At that time, this omega value will be equal to the synchronous speed, right? Let's say in this point, the fault or disturbance actually has been experienced. Now, this omega value will vary over the time. Let's say after some moment, it is again comes back to the previous system. That means again now the omega value is omega x, right? So if this is the scenario, then we will call the system as transient stable, because let's say this disturbance was due to the large or severe disturbance. Okay. So if this system experiences a large disturbance and after that if it is able to again come back to the synchronism, then we will call it as transient stable system. If not, then this is the transient unstable system. And there are many examples for large disturbances or severe disturbances. The first one is the sudden application of load. That means, let's say we have load demand PD and our system or the combination of many generators are supplying this PD that is equal to PD. Let's say at a certain moment the load has been increased, okay, suddenly from the customer end. That means now this PD is higher than this PD. If the increase of this sudden load is used in terms of magnitude, at that time it can be termed as the large disturbance. Okay. Then the second example is the loss of generation. That means let's say we have 10 generators in the system and all of these 10 generators are combined in giving the power supply P. So if for example 3 or 4 generators actually go out of the synchronism or actually go out of the system, at that time this generation will drop, right? So we will not be able to match the demand. At that time that disturbance can be always a severe disturbance or large disturbance. Third point is the loss of large load. It is actually the opposite of the first point. Here, the application of large load, and this is the loss of large load. Means let's say suddenly the customer has turned off many appliances, right? Now the demand has increased suddenly. So at that time again there will be some kind of imbalance between this P and PD, and that disturbance can be again called as the large disturbance. Okay. And the fourth one is the example of internal and external fault in the system. So what are the external faults? Like the line-to-line fault, the three-phase fault, this type of faults are actually the external faults. And internal fault means the short circuit fault or the insulation failure inside the machine. So if this type of external or internal faults occur to the system, at that time that can also be treated as large disturbance. Now, how we can solve the transient stability? So, from our previous slide, whenever we solved the small disturbance stability, we found these two equations, right? And that two equations were actually the analytical equations, right? The solution were actually the analytical solutions. That means inside those equations there are some terms, right? If we put all the terms correctly inside those equations, then we will get the exact result of this delta of t and omega of t, right? But to solve the transient stability scenario, we can apply the analytical method. That means this analytical method is not applicable here. Okay? So what are other options? We can take help of numerical methods or graphical methods. Okay? And inside the numerical methods, we can take help of Euler method, modified Euler method, or let's say Range-Kaplan method. Okay? So all there are other numerical methods, and all of these numerical methods you have learned in the previous semester, right? So you are already familiar with this. So all the algorithms have its own advantages and disadvantages, okay? Because there are trade-offs between the computational time as well as the accuracy. Okay? Let's say Euler method, so the simulation time is very much less for this Euler method. That means in terms of computational time, this algorithm is faster, but in terms of accuracy, the accuracy is less, right? For this Euler method, this is less, this is faster. Okay, we will see that thing because here there will be some complex systems. Okay, so those things we can actually represent analytically. We will see the scenario later on. Okay, but what I am trying to say that like the small disturbance stability, we can apply the analytical method. Our option are two: either we can go for numerical methods or we have to apply the graphical method. Okay, so Euler method, the computational time is less but the accuracy is low. So if we now go to the modified Euler method, maybe the accuracy will be higher, right? But again the computational time will be higher, so it will be slow, right? So like this, each algorithm has its own disadvantages and advantages. Okay. Then the graphical method, and the most commonly used graphical method to solve transient stability is the equal area criterion. Okay. And in short, it is called EAC, equal area criterion. And actually, in this slide, we will not use the numerical methods, rather we will use this graphical method to solve the system. Okay. We will see how easily we can solve this transient stability using this graphical method. Okay. So, in summary, in this slide, we will actually apply the graphical method to solve the system. So, what is the advantage of equal area criterion method or the EAC method? Actually, this provides quick prediction of transient stability. That means just by looking at the graph, we can say that whether the system is transient stable or not. Okay, we do not need to solve the system. We can just look at the graph and we can easily say that, okay, or we can easily sense that this is a transient stable system or not. Okay. Then there is no need to solve the swing equation analytically or numerically. Right? If you want to solve the equation analytically or numerically, then maybe it will be a huge task, right? But if we use the graphical approach, that will be very much easier in terms of simplicity, right? But there are some limitations. The first limitation is that this method is only applicable to one machine system and for two machine systems. Okay. So if our system contains more than two machines, like 3, 4 or 5, then this EAC method is not applicable. As in this slide we are considering about the single machine infinite class system, so there is only one machine, right? So we can easily use this method, EAC method. Then EAC is based on the graphical interpretation of the energy stored in the rotating mass. Okay. So energy stored in the rotating mass. What does it mean? So what is actually the rotating mass? So this is our single machine infinite bus system. This is synchronous generator, transformer, double circuit line, and this is infinite bus, right? You know the concept of infinite bus. Actually the voltage, magnitude, frequency and angle, all the parameters are constant here, right? So, can you say which in this system, which one is the rotating component? The generator, right? Because the rotor of the generator will rotate. So, this is our rotating component. So, that means the energy stored in the rotating mass means the energy stored inside this generator. Okay. What does that energy? So let's say we are giving the mechanical input and we are getting the electrical power, right? So the difference between two will be stored inside the rotor. Okay, and depending on that, rotor will either accelerate or decelerate. Let's acceleration in the rotor node. If the case is opposite, then there will be some deceleration, right? We will see these things in details, no problem. I am just giving you a recap. So that is actually written here in this line that ESC is based on the graphical interpretation of the energy stored in the rotating mass. Okay, have you got the idea? We will see in details of this thing, how the energy is stored here and how we can calculate that stored energy. We will deal all the things. Okay.
Generator is indicated.
Yeah, the generator means the rotor of the generator.
Rotor of the generator.
Because the only moving part is this generator. Other part are not actually moving. Then the swing equation for this SM system will be this, right? You know this thing. This is the swing equation. Look, probably you have seen this term in the right side, but if you take it in the left side, it will be like this. And this is the acceleration of the rotor. That is the tau derivative of this delta. It will be simply the difference between Tm minus T. Okay. Now let's take this term in the right side. Then we will get equation number 2. D square delta over dt square pi f naught over a is Tm minus T naught. Okay. Then we want to multiply this term in both sides. 2 d delta over dt. Okay. Why? The reason will be clear after a few lines. Okay. So after multiplying, we are getting 2 d delta over dt here, and 2 is here in this side, and d delta over dt is here. Okay. So now this term, this one, whole term can be written as this. Can you not tell me how we can write this as this? What is the logic behind this?
Previous one is the
considering d delta dt as a derivative.
Exactly. So let's just think about this term. Let's start with this term. So this is the differentiation of this term, this whole square term, with respect to dt, right? With respect to time. So how can we differentiate this thing? We should apply the chain rule, right? That means, look, this is not t, but we will assume this whole term as t. So it will be t square. So what will be the differentiation of t square in terms of t? 2t, right? So 2t. T is not t here. T is actually the d delta over dt, right? But we assume this as t, but this is not the actual t. That's why again we have to put the derivative of this term in terms of t over dt, right? So that will be t over dt of d delta by dt, right? Now these two terms can be written combinedly as d square delta over dt square, and here we have d delta over dt. Okay. Have you understood how we can combine these two terms into this? Now look, this and this term are actually same, right? Have you understood this thing? So that's why we have multiplied this term to d delta over dt on both sides, so that we can apply the chain rule, and finally so that we can get this thing. Because from this expression we want to know the value of d delta over dt. Okay, that's why we are approaching like this. So and the right side it is same as before. There is no change. So now let's in the both side we have dt, right? So we can eliminate this, right, from the both sides. Then we will have d delta over dt whole square equals to 2 pi f naught over h Pm minus P d delta. Okay. Now we can integrate this equation in both sides. Right? In the left side, this integration and this d term will be cancelled by each other, right? And there will be only d delta over dt also. So look, equation number 6. Integrating both sides of equation 5, we will get this. On the left side, we will get d delta over dt whole square, and in this side, this will be the integration. Okay, and this is the constant term, so we can take this term out of this integration. That's why it is here. Then this is the integration. Okay, and we should set the lower limit and the upper limit, right? And we are doing the integration in terms of delta. So the lower and upper limits will also be in terms of delta, right? So let's say the lower limit is delta naught, right? This is the initial value of delta. the lower limit, and let's say the upper limit we have set it as delta. That is an arbitrary value. Okay. So now if we do the square root with both sides of this equation 6, then we will get equation 7. Okay. Equation number 7. Then from the previous knowledge, we know that our d delta over dt is actually the omega minus omega 0. Can you recall this? Because this is the derivative of the rotor angle, so we will get the angular velocity, change in the angular velocity, right? What is this omega? Omega naught and this delta. Okay. Let's refresh your memory from the previous concept. Let's say this was our stationary reference frame, right? And the speed of this reference frame was 0. Then we added one synchronously rotating frame, which speed was omega s, the synchronous speed, and it was rotating in anti-clockwise direction. And also we had the rotor position. This is the rotor, and the rotor speed is omega, right? And this is also rotating in anti-clockwise direction. What was the angular difference between this rotor and this stationary frame? It was theta, right? And the angular difference between this rotor and this synchronously rotating frame was this was delta, right? Whenever we are in the steady state, at that time this omega is exactly equal to omega s. At that time there is no change in delta over the time. But whenever there is any disturbance, at that time this omega will take different value than this omega s, and we will see some kind of dynamics in the delta behavior, right? That is the next. So here this is omega. Omega is actually the rotor speed, and omega is the synchronous speed. Whenever we are at the initial stage, at that time we can refer the rotor speed as omega naught, and actually this is equal to omega s, because at the initial stage we are in the steady state regime, right? So this omega s can be termed as omega s, that is the synchronous speed of this rotating frame. That's why this term is called the relative motion of the rotor with respect to a synchronously rotating frame. Because this is omega, this is omega naught. Omega is the rotor speed, and omega naught is the speed of the synchronously rotating frame. That's why this actually represents the relative motion of the rotor with respect to a synchronously rotating frame.
So what is omega naught here?
Omega naught is the initial speed of rotor. Let's say at just time t equals to 0 plus at this time. Okay. So at that time there was no disturbance. We will say that at the initial stage the system was in the steady state. Okay. So at that time this omega naught is actually the omega s, right? So this is the relative motion of the rotor with respect to the synchronous rotating frame. Now just comparing these two equations 7 and 8, we can write that this term is equal to actually this omega minus omega, right? Because this is d delta over dt, this is also d delta over dt. The same term. This is omega minus omega. That means it is written that in equation 7, this equation actually represents the relative motion of the rotor with respect to a synchronously rotating device. Have you got the idea of this point? Now let's come here. Now before coming to this slide, I want to just give you some idea about different phase of this system. Let's say at the initial stage the system was at steady state, right? This is the steady state system. So at that time our omega was equal to omega naught. That was equal to omega s, right? So in this stage, what will be the relative motion? It will be 0, right? So if this is 0, this and this is equal to this, right? So this term should also be 0. This after doing the squaring both sides, we can remove this square root term, right? Also we can remove this constant term, so only this term will remain. So this term should be equal to 0, right? Delta naught delta EL minus PE over d delta. This should be equal to 0. Have you understood this thing? Because this is 0, omega minus omega naught is 0, that means this is actually equal to 0. Then to the square, this square root will be removed, and then twice by f naught over h, you can just take that side in the right side, so it will be simply 0, and then you will get only this integration term is equal to 0. Okay. Then let's think about the disturbance space. Now there is some disturbance, so obviously this omega and omega naught is not same. So omega minus omega naught will also not be equal to 0, right? So this term, this integration term will also will not be equal to 0 as well, right? So this term will not be equal to 0. Now let's say post fault or post disturbance is, and we are considering that after the disturbance again the system is coming back to its original state. Again the system is transient state. Okay. That means again after the disturbance we will see that the rotor speed is again equal to the synchronous speed. That means the relative motion will be equal to 0. Then again this integration term will be equal to 0, right? All of these things that I have shown here is summarized here. Okay. Look, for stability, the rotor should regain synchronism after the disturbance, right? To have the stable system after the disturbance, our rotor should again regain the synchronism, right? That means the rotor speed should become synchronous speed after the disturbance. Okay? That is to say that after the disturbance, the relative motion omega minus omega naught should be 0, right? That is actually the d delta over dt, because this is actually the omega minus omega naught, right? So this should be 0. Means that our rotor speed should be exactly equal to the synchronous speed, and we can write this thing. This is that this integration is actually equal to 0. And this equation number 9 is called the equal area criterion for stability. Okay. Why the name is like that, we will actually discuss word by word later on, no problem. Just for the time being, just realize that, okay, what is actually this integration? Let's say we have the P versus delta curve, right? So you know this thing. Let's say this is from 0 up to pi. We are considering the generation rule. So how can we plot Pm here? Simply a horizontal straight line, right? Because Pm is not changing with respect to time. It is independent of delta, right? So Pm is independent of delta. That's why we can just plot the Pm using this horizontal line. Okay. Now, what does it mean? Look, the integration of some term under this term. How? The whole limit is delta naught. Let's say this is delta naught, and let's say this is what? Delta. Let's say this is the delta. Okay. That means inside this region, we want to do the integration of the difference of this two. So what is the difference? This is the PE, this is the PM. The difference will be this. So if you do the integration, you will see this type of thing. What does it represent? Some area, right? This is some area. That's why the area terms come here. Okay, this is the area, equal area fraction. Why equal? That thing we will also explain later on. Okay. Also this concept, how this is actually area, this we will show here also. Okay, how this is actually area. But have you understood this thing? That the integration under the curve will give you some area, right? Yeah. Exactly. Okay. In this case, actually, this is actually P minus Pn. Okay. Integration of P minus P. This case. Whenever we will discuss this case, we will see the Pn minus P. Because I am giving you the idea that this term is actually the area, right? The integration of something that is under some term that will give us some area, right? Obviously, this is actually the most appropriate way will be the P minus PM, right? This thing. So we'll see this thing here. No problem.
So delta naught when E is equals to PM, do we get delta naught at that point?
All the things I will discuss here. Okay? I'm just giving the summary here. Okay? So just let me finish this slide. Then if you have any question, you can ask. Okay? So this equation is actually the ESC for stability. Okay? Now let's go to this slide. So up to this slide number 8, we have discussed some introductory things of this transient stability slide. From this slide, we will see how we can solve the transient stability using this graphical method, that is the ESC. Okay? And this is very much interesting. If you just follow the lecture, you will see that these things are actually very much easy. Okay? Comparatively to your previous slide, that is this more disturbance. Whenever we dealt with the analytical solution, we have to do lots of calculation. But if you apply the graphical approach, then actually it is very much easy. You can just play with the graphs and you can find the errors. Okay. So this is the P versus delta curve. Okay. For any synchronous machine. Consider a synchronous machine initially operating at equilibrium, and that point is A. So it is said that this is our equilibrium point at the initial stage. Okay. And in this point, our Pm is equal to Pe. So this is the initial value, that's why it is written as Pm0 and Pe0. So in this point, what is the Pm0? This straight line, the horizontal straight line. This is actually our Pm0. Okay. And how we will find the Pe0? We have to look for the intersection between this line and this power intersection, right? Then we will get this point, point A. So in this point, our Pm and Pe both are equal. Okay. Both are same. Now next point. So in this point, what is our rotor angle? We have to go downward, and along this x-axis we will get this curve, right? And this initial rotor angle is represented by delta naught. So the initial rotor angle is delta naught, and this delta naught can be calculated using the relation of this. Okay. How we can calculate this? Look, we know that Pe naught should be equal to P max sin delta naught, right? So what will be the value of delta naught? It will be sin inverse Pe naught over P max, right? And in this point, the P naught and Pm naught are actually same. That's why you can write like this, that delta naught will be equal to sin inverse Pm naught over P max. Okay? Have you understood this thing? And what is your P max? P max is the magnitude of E prime, magnitude of V over x equivalent. What is x equivalent? This is your SM prime system, and you can calculate the x equivalent from here, right? Addition of this, and the parallel combination of this. So the parallel combination of these two will be x1, 2 over 2, because these two values are same. So the addition of this, and this will give you the x equivalent, right? Also in the last class, during solving the example 11.2, we saw it, that how we can calculate the x equivalent. So this is the x equivalent, xt dash plus xt plus x1, 2 over 2. Okay. Now, if you have the information of the magnitude of E prime, the magnitude of V x equivalent, okay, then you can calculate P max. Also, if you know the Pm0, then you can calculate the delta naught. Okay. So, if you have all the information in your hand, you can easily calculate this delta naught. So, this is our point A. So, this point is clear to you. Second point, the initial rotor is delta naught and can be calculated using the relation of this. Okay. And also at point A, what will be the speed here? The rotor speed. It will be the synchronous speed. That's why the rotor speed here is actually omega. That thing has been said here. That in point A, the rotor speed will be omega. Now, the point number 3. Now consider a sudden step increase in input mechanical power represented by the horizontal line PMO. Previously, what was the level of mechanical power input? This is 20. Now we are increasing it, right? Increasing it means line will now shift towards the upside, right? Now this is our new PM, that is the PM1, this horizontal line. Okay. Now point number 4. Now this PM1 is higher than PE0. Now using this swing equation here, it will be what is PM now? PM1, and what is PE? PE0. PM1 is higher than this PE0, so we will get this difference as a positive value, right? So if this is positive, what will happen to the rotor? Will it accelerate or decelerate? It will accelerate, right? Because you will get some positive value in the right side, and in the left side you have the information for your rotor acceleration, right? So the rotor will accelerate, right? Have you understood up to point 4? Now point 5, as the rotor is accelerating, what will be the value of delta? Will it increase or decrease? Obviously it will increase, right? The delta value will increase. So if delta increases, will the delta go in the right side or left side? Obviously the right side, because in the right side we are getting the higher delta, right? And we know that this P depends on the value of delta, right? Using this equation. So if delta increases, what will be the value of P? It will also increase, right? Actually this is true for this range. If your delta is up to 90 degree, then you can say that okay, with the increase of delta, you will get increased value of P. Okay. That's why as a result, delta increases and consequently P increases. P will increase following which path? Like this or following this power angle curve? Obviously following this path, right? Following this path, P will increase. Okay. So look, the P increases along the P versus delta path. That is the along the AB path. Along this portion, now in this portion, if you want to calculate the rotor speed omega, obviously it will be higher than the previous synchronous speed. Why? Because the rotor is accelerating, right? Acceleration means you will get the rotor speed higher than your synchronous speed, right? That thing is written here along this portion of this curve. Your omega is higher than omega. Okay. Now this P is increasing, also the delta is increasing. After some time, this delta value reaches the value of delta 1, that is in point number B. And once this delta comes to this point, your P becomes exactly equal to PM1, right? Now, will there be an acceleration in this point? No, right? Because now again apply the swing equation formula. Now PM1 and PE0, this P now is here, right? So these two values will be now same. So this will give us 0. So there will be no acceleration. Means that our system is again coming back to its steady state condition, right? So that means actually from here to here, the P value increases and it actually tries to catch up the value of PM1, so that the system can be more to the steady state. Okay. Have you got the idea? So if I do the summary, then actually what I am trying to say that this is point A, this is the equilibrium at which our PM0 was equal to PE0. Okay. And in this case, the rotor angle is delta naught and the rotor speed is omega naught. That is the synchronous speed. Then we have applied a higher amount of mechanical input power, that is the PM1. Now PM1 is here. So due to this swing equation, the rotor will accelerate. Means the delta value increases. The delta will increase in the right hand side. If delta increases, P also increases following this path. Okay. And whenever the delta will come to this point P, that is the delta 1, at that time the P is equal to PM1. That means the system will again come back to the steady state. Okay. This is the scenario that has described in these points. Okay. Now look here. Let's say our input mechanical power is PM1. Okay, but here this is P. Okay, so obviously there is some PM minus P over here, right? Because here this is P, this is PM, so you will get some PM minus P. Then in the next time instant, this is P, right? This is P, but what is your PM? This is your PM. So you will get some difference here as well, right? In the next time instant, you will get another difference. You can accumulate all these differences and you can add up those, right? Then you will get all the excess energy, right? That is the PM minus P that will store inside the rotor. So is it a smart idea that if we will calculate all of this instant and then we will add up, or we will use any other smart tool, we can easily take care of the integration, right? That's why this is the integration. How do we do the integration? PM minus P, right? So which PM value should we take? Obviously this PM now, right? We want to take the difference between this and this, okay? And in between point A and B, that is in between delta naught and delta 1, right? So this is, that's why PM1 and minus P. So how can we write P? P will be the function of delta, so it will be simply P max sin delta. Okay, this is P. Then the integration will be in terms of d delta. And how will we write the lower limit and the upper limit? It will be from delta naught to delta 1. Okay, this is delta naught, this is delta 1. Okay, so this is your complete integration, and this thing will give you this area, right? The area under this PM1 and this RP in between delta 1 and delta 1. Okay, that is the area ABC. Okay, area ABC, and this area can be treated as area A1. Okay. Have you got the idea? So now that means this integration is actually representing some kind of area. That's why it is called the equal area, right? Okay.
Sir,
Now,
which point are we getting P max?
P
Max.
this P max.
So just P, sir. At the top side.
Yeah,
We get PM1. Where do we get the P?
P. Actually, this is our P. Okay, this is our P. That is the function of sin delta, right? So look, here it was P naught. Then the P increases along this path. Okay, but you can write simply PM1 minus P. Instead of writing like this, we are replacing this P in terms of P max sin delta, because this delta will not vary from delta naught to delta 1, and you will get different P here, and you will get the differences at each step. Okay, and that is the integration which you will just accumulate those and you will add up this. Okay. So, okay, do you have any confusion up to now? So this is your area 1. Okay. Now, in the next journey, we will see that we will find another area, and that area will be equal to area A1. That's why it is called the equal area patch. Okay. But we will not go that journey today. Inshallah, in the next class we will see the next journey. Okay. So in today's class we have covered up to point A2, and from this we can indicate the difference